key to understanding hydraulics is Pascal's principle. When an external pressure is applied to a fluid, the pressure will be transferred to all parts of the fluid. Okay, first of all, we're not talking about just regular pressure. So if you're standing between this pond and this well, you have atmospheric pressure on you. We talked about that the other day. It's basically the weight of the air, which is 1 times 10 to the 5th Newton per meter squared, or pascals. Now, if you stand at the bottom of this pond, you have, in addition to that atmospheric pressure, you have the water pressure. The water pressure is rho GH, where rho is the density of the fluid, in this case, water. And so you would have the density of water, which is 1.0 times 10 to the 3rd meters or kilograms per meter cubed. And then you would multiply that by little g, which is 10 meters per second squared, and then the height. So let's just say the height was 10 meters. So then the pressure of the water would be the 1.0 times 10 to the 3rd times 10 for little g, and times 10 meters for the height, or 1 times 10 to the 5th. And then you would have to add the 1 times 10 to the 5th atmospheres, and you would end up with 2 atmospheres. That'd be the pressure if you were at the bottom of that pond. So it's important to realize that pressure, water pressure, only depends on the height and the density, and little g, which is always a constant. So if you're standing at the bottom of this well instead, and the well is 20 meters deep, even though there's significantly less water in the well than in the pond, the area doesn't come into play. So essentially you'd have twice the height, you'd have twice the pressure. So you'd have 2 atmospheres just of the water plus the atmospheric pressure above. So Pascal's principle is different. Look at this piston. If you have a force applied by the piston, that's an external force. Let's say our external force is 30 newtons and the area of the piston is 1 meter squared. We could say that's 30 pascals. And that pressure could be felt anywhere in that container, because remember, it's non-compressible. So at the very bottom, you'd have 30 pascals. You'd still have the rho GH, you'd still have the pressure caused by the water, but you'd have that initial pressure from the top. Or if you're at the very top, you'd have 30 pascals. Let's say we had a glass tube here, and it's a vacuum tube, and we stick that into a bowl of mercury. Okay, so I'm just showing the mercury. Well, because there's a vacuum, the mercury is going to go up into the glass, and I'm showing the mercury is rising above the surface. Well, why am I doing that? Well, there's an outside pressure. It's the atmospheric pressure, which is 1 times 10 to the 5th pascals. And because there's no pressure inside, because it's a vacuum tube, we have more pressure, and that extra pressure is what is going to raise the height of the mercury in that column. Okay, now because of Pascal's principle, we can say rho GH of the mercury in that column has to equal the external pressure, which is 1 times 10 to the 5th pascals. And if mercury is 13.6 times the density of water, we could just do the math here. Don't forget, little g is 10 meters per second squared, and the height here is what we're going to solve for. Set that equal to 1 atmosphere, or 1 times 10 to the 5th pascals. We find the height is 0.74 meters, or we could just say that's 74 centimeters of pressure. Essentially, that is what we've created is a barometer. That's what a barometer is. It measures the pressure of the outside atmosphere. Okay, so now we're going to do a practical problem. This is a lift system in a garage. It may not look like it right now, But the lift system is going to use hydraulics. It's going to have an input cylinder and an output cylinder. And the car is going to end up being above the output cylinder. Now, I say cylinders, and the output cylinder has a diameter of 30 centimeters. The input has a diameter of 10 centimeters. And we would need to fill this with a usually like a brake fluid, like a .3 brake fluid. So something that is obviously not compressible, but also has a lubrication feature to it. Okay, and so usually this part is under the ground, and the car is going to sit on this contraption, which is attached to the output cylinder. So that is a crude drawing of a car. So what we're going to try to do is just use pressure on the input cylinder. In fact, usually what they use is just the air pressure, the same air pressure that they would use to fill a tire. So they have a hose with air pressure, usually around 30 psi, and that's generally what they use. So this is the hose is the input pressure, and that's essentially going to lower the left side here. That fluid is going to get forced down the input, and it's going to get forced up in the output. But because the output has a bigger diameter, you're going to have less height on the output. So you're trading height for area. Okay, so the key here is using Pascal's principle, which says as long as we're talking about an outside pressure, the pressure at the input has to be the pressure at the output. In fact, it's the pressure anywheres along the way. Well, we could say the pressure of the input is just the force at the input over the area of the input. And the output would be the force of the output over the area of the output. Let's take the weight of the car to be about, a typical weight of a car would be about 14,000 newtons. Okay, and if we want to find the input force to lift the car, we would say the input force, just doing some basic algebra here, would be the 14,000 newton output force times the ratio of the area. So it'd be the input area, pi r squared. So if D was 10 centimeters, r would be 0.05 meters. Of course, you have to square the radius. And then you divide that by the output area, which would be pi, times that radius, which would be 15 centimeters, or 0.15 meters squared. So the pi's cancel. And if you just do 0.05 squared into 0.15 squared, you realize it's a value of 1/9. So the input force is going to be 1/9 the output force. So if the output force was 14,000 newtons, the weight of the car, you would have to push on the other end with about 1555.5 newtons to be exact. So this is essentially giving us a 9 times mechanical advantage. So we're able to multiply the input force by 9. This sounds fantastic, but remember, it's a trade-off. Work is force times distance, and in this case, the distance is the height. So we're trading height for force. So the input cylinder has to go down 9 times what the output cylinder is lifting up. Because remember, volume is area times height. And just to confirm what the input pressure is, remembering that pressure is just force over area. So if we just take the force, which is the 1555.5 newtons, and divide by the area, which was pi times 0.05 squared, we come up with something that's pretty close to 2 atmospheres. Just do the math here. We get just about 1.98 times 10 to the 5th pascals, which is just about 2 atmospheres. And 2 atmospheres also is just about equal to 30 psi, which once again is readily available in most garages.